Hello and welcome to our Essentials of Semiconductor Device Physics course. Our topic today is band theory. In lecture 2, we learned that when a wave is confined, its states are discretized. And we also learned that according to quantum mechanics, electrons have wave properties, so their states are also discretized when electrons are confined. And we found the energy of an electron that is confined in a 1D quantum well, in other words, in a one-dimensional box. And we find that these energies are given by this expression where h is Planck's constant, m is the electron's mass, L is the length of the quantum well, and C is a natural number indexing the state. So C equal 1 is one state, C equal 2 is another, and so on. And in lecture 7, we extended the idea to a three-dimensional box, in other words, a cube, and we found that now the states are labeled by three natural numbers. So 111 is one state, 112 is another, and the energy of each state is given by this expression. And then later on, we started using the term orbital to denote the state of an electron. So, for example, 111 is an orbital, 112 is another orbital, and so on. Now, when we consider an atom, we find a similar situation. Electrons in an atom are confined. They are confined by the force exerted by the nucleus. So if they are confined, their states are also discrete. And these states are the atomic orbitals, which are labeled by the letters S, P, D. So in this lecture, we need to consider atoms, but we are not interested in looking at details of the orbitals. So we're going to simplify the discussion as much as possible, and to do that, we're going to consider a simplified atom. So we're going to consider only two orbitals. We're going to suppose there are only two orbitals of interest in the atom. And I'm representing these two orbitals graphically here. So this axis is the energy. So this would be one orbital, this would be another orbital, and the energy of this orbital is higher than the energy of this orbital. And in this lecture, we want to look at what happens to these orbitals and their energies when we let one or more atoms interact, forming chemical bonds. And we are particularly interested in finding what happens when many atoms interact, forming a solid. But to make the discussion more intuitive, let's first consider a spring mass system. So in a spring mass system, the mass oscillates in a well-defined frequency, which we call resonance frequency, and is given by the square root of the spring constant divided by the mass. If you don't know where this equation comes from, don't worry, we don't actually need it in this lecture. I'm just showing it here for the sake of context. But it's okay if you have never seen this before. What matters is that the mass will oscillate at a well-defined frequency. So another name for this kind of system is harmonic oscillator. So the harmonic oscillator is analogous to an atom in the sense that the electrons in an atom are confined by the nucleus, and in a harmonic oscillator, the mass is confined by the spring. So the oscillation of the mass plays the role of the orbital. And the resonance frequency plays the role of the energy. The main difference between this system and the atom is that in a single atom there are many orbitals and many energies. And we are considering at least two orbitals. But in the spring mass system, there is only one mode of oscillation, so only one orbital and one resonance frequency. But if we understand what happens with harmonic oscillators, we will understand what happens, at least qualitatively, with atoms. So let's begin by considering two independent harmonic oscillators. And I'm showing here the orbital of this harmonic oscillator, so the mode of oscillation with its resonance frequency, and I'm showing here the same for this harmonic oscillator. So in this case, we have two harmonic oscillators, so we have two modes of oscillation. We have two orbitals. And both orbitals have the same resonance frequency because we're considering two identical harmonic oscillators. Now if we treat the entire system as one single system, then we can say that this entire system has two modes of oscillation, two orbitals, with the same resonance frequency. So here I'm representing in the same graph the two modes of oscillation. So this line represents the mode of oscillation of this harmonic oscillator, and this line represents the mode of oscillation of this harmonic oscillator. So there are two orbitals, two modes of oscillation with the same resonance frequency. But usually we represent these two modes of oscillation with the two lines overlapping each other. So in this case, we still have two modes of oscillation. We still have two lines here. We can only see one because they are overlapping each other, and they are overlapping each other because their harmonic oscillators are identical, so they have the same resonance frequency. Okay, so this is a representation of the modes of oscillation of the entire system. We have two modes of oscillation because this mass can oscillate and this mass can oscillate. But since they have the same resonance frequency, we can see only one line here, but there are actually two. Now recall that our goal is to find what happens to orbitals of atoms when the atoms interact. So in our analogous system, the interaction is represented by a coupling spring, and omega here is the coupling spring constant. So when we have a coupling spring, we still have two modes of oscillation. The coupling does not change the number of modes of oscillation. It does not change the number of orbitals. But it does change the resonance frequencies. So in the textbook, this system is analyzed in more detail. But if we do this analysis, we're going to find that there are two modes of oscillation of this system. One of them still has the same resonance frequency as before, and the other one has a higher resonance frequency given by this equation, which is derived in the textbook. But we're not going to derive here because we want a qualitative analysis. So the effect of coupling is not to change the number of modes of oscillation. We still have the same number of modes of oscillation as before. But the effect of coupling is to change the resonance frequencies. Before coupling, the two modes of oscillation had the same resonance frequency. The two lines were overlapping. Now the lines are no longer overlapping. One mode of oscillation has a higher resonance frequency. So the mode of oscillation that has the same resonance frequency is the mode when the two masses oscillate in such a way that the coupling spring is at rest. And this mode of oscillation with a high resonance frequency is when this mass moves in this direction while this one moves in this direction and then back. So if you want to know more details about the modes of oscillation, you can take a look at the textbook. But here for us what matters is that the effect is to change the resonance frequencies. Now when we consider atoms, we have a very similar situation. Here I'm representing two identical atoms that are sufficiently far away from each other so that one atom does not affect the orbitals of the other atom. So this is a physical situation that is similar to the two spring mass systems when there is no coupling spring, when they are independent. And since we're considering two identical atoms, their orbitals will have the same energy. We could also consider a system formed by these two atoms. So in this case, there are two orbitals of this system with this energy and two orbitals of this system with this energy. So here we have two lines and here we have two lines. So for example, one line here could represent this orbital and the other line here could represent this orbital. Since the atoms are identical, these orbitals have the same energy. So the two lines are overlapping each other. And the same idea applies here. We have two lines overlapping each other. So we have four orbitals in this system formed by the two atoms when they are sufficiently apart so that one does not interact with the other. Now when we let the atoms interact, when they are sufficiently close so that one atom affects the other, then the orbitals will be modified. For example, I'm representing here a possible orbital of the system formed by the two interacting atoms. This orbital does not look like any of the orbitals of the isolated atoms. It does not look like this orbital or this orbital. If it's a different orbital, if it's a modified orbital, then the energy is different. So in this system where the atoms are coupled, we still have four orbitals. We have not changed the number of orbitals, but we have changed the energies. So now each orbital has a different energy from the others. So that's the effect of coupling. The effect of coupling is to modify the energy. Now suppose we begin with one atom and we consider two orbitals of this atom. And then we bring another atom and let this atom interact with the first atom. So since we have two atoms here and each atom has two orbitals, we're going to have four orbitals in total. And since the two atoms are interacting, the energies are modified. Now suppose we bring a third atom. Now we have six orbitals and the energies are modified. So as we increase the number of atoms that are let to interact, we are adding lines in this region representing the orbitals. So when you go towards a macroscopic number of lines, the spacing between the lines will be so small, we're going to have so many orbitals in a region that we could treat this region as if they formed a continuum. And that's what I'm representing here. So this region, where there are so many orbitals so close to each other that we could consider them as forming a continuum, is what we call a band. So here I'm supposing that this region formed a band and this region formed another band. But it could well be that they merge together. It could well be that these two bands connect. It depends on each situation, but it is not our purpose to study in detail how the bands are formed. We're going to take them for granted, as a given. Okay, so we have been discussing the formation of the bands from the orbitals. But now let's take a look at the occupation of these bands. So let's suppose that we start with an atom where both orbitals are occupied. So we have one electron here, one electron here. When we bring another atom, we're going to have four orbitals and four electrons. So all orbitals will be occupied. The same with three atoms. We're going to have six electrons, six orbitals. So in this example, when we form a solid from this atom, and if we still consider that this region formed the top band and this region formed the lower band, in this example, both bands will be fully occupied. All orbitals inside the band would be occupied. But that does not need to be the case. It could be that we begin with an atom where this orbital is occupied and this one is empty. Then we're going to have these two occupied, these two empty, and then if we still consider that the top region will form the top band and the region in the bottom will form the lower band, in this example, the lower band will be completely occupied, but the top band will be empty because these orbitals in this example are empty. And it could be that we have a partially occupied band. For example, we could have one electron here and this orbital unoccupied, and it could be that the two regions join, they connect each other, forming, for example, this band. In this case, the band will be partially occupied. So we could have, for example, this band fully occupied and this band partially occupied, and you could have this band partially occupied and this band empty. So all situations can happen. It depends on the material, it depends on the chemical bonds, but it's not our job to find or to study how what properties lead to what kind of occupation and what kind of band. This kind of study it pertains to solid state physics. So this is a typical situation that is analyzed in solid state physics. But in our course, we're going to study what are the consequences of each situation to the electrical properties of the material. So we're going to take the bands as given and their occupations as well as given, and we're going to analyze what electrical characteristics we should expect from each situation. But we're going to do that in the next lecture, when we will also define what is a semiconductor, and we're going to take a closer look at the two types of charge carriers in semiconductors, free electrons and holes. So see you next time.